All right, we're gonna wrap up the chapter today and talk about the rational zero theorem. So we're gonna put a lot of the skills that we've been building and developing and learning into play with finding and identifying the possible rational zeros of a polynomial function and then finding them. All right. So when we identify the possible rational zeros, this is the actual rational zero theorem right here. This is what we're going to be doing, okay? So this is identifying the possible rational zeros is the rational zero theorem, okay? And remember, rational zeros are the roots or the x-intercepts where the graph crosses the x-axis. So the rational zeros are the roots. They are all real. They are where the graph crosses the x-axis. We can find all the rational zeros of a polynomial function with these steps. We're going to use, number one, the rational zero theorem, okay? Which you'll hear about in a second. Then, after we use the rational zero theorem, we're going to apply Descartes' rule of signs, which you just learned in the last lesson. We're going to use synthetic substitution to find a 0 or 2. And then we're also going to use factoring, except in other algebraic techniques for solving for x. Oops. Forgive my misspelling there. Solve for x. There we go. So you're putting a lot of skills together. It sounds kind of hard, but it's just a process. It's steps, and I'm going to give you those steps as we go. So the rational zero theorem is a theorem that states if the ratio of p over q is a rational number in simplest form, so it's just a fraction, and is a zero of a function y equals f of x, then p is a factor of the last term, the constant term, and q is a factor of the first term, the leading coefficient. So remember, the leading coefficient is the coefficient of the highest degree of a function. So in addition, if the coefficient of the x term with the highest degree is 1, so the leading coefficient is 1, then any rational zero of the function must be factors of the constant, factors of the last term, which is the constant. That's called the integral zero theorem. So it's just kind of like an addition, kind of like a corollary in geometry. So for example, we're going to list all the possible rational zeros of this function f of x equals 2x cubed minus 11x squared plus 12x plus 9. Okay, so this is in descending order of degree, and so the constant is 9. That is considered your p value, okay? The leading coefficient is 2. That's considered the q. So I just identify those right away. So p over q. P is a factor of 9 or so, and q is factors of 2. So all the possible p's are, and it's positive and negative factors. So plus and minus 1 is a factor of 9, plus and minus 3, and plus and minus 9. And then all of the factors of q, which is 2, plus and minus 1, and plus and minus 2. So that's the first thing you do, is just list out all of the factors of the constant p and all of the factors of the constant q, and then we write those as ratios of p over q. So plus and minus 1 over 1, 3 over 1, 9 over 1 first, and then plus and minus 1 over 2, 3 over 2, 9 over 2 second. I always write the integers first and the fractions last. It's just a matter of my process of making that list a little easier. So why we don't repeat, and we always simplify fractions. So p over q, don't repeat because you're making a list here. So don't repeat and always simplify. So this list, what is this? This is a list of all of the possible rational zeros of a function. So now if you're given a function like f of x, like this function right here, we know there's 3 roots because it's a 3rd degree function, but right now there is an infinite list of what those roots could be, right? Because we have an infinite list of real numbers. So what we've done is we've taken that infinite list and we've narrowed it down to this list of 1, 2, 3, 4, 5, 6 times 2 is 12 because we're positive and negative. So now we've gone from an infinite amount of possible rational zeros to 12 possible rational zeros. So that's why this rational zero theorem is helpful. So you're just going to practice the theorem and then we'll move on, okay? So please do 1 and 2 on your own. Just list the possible rational zeros for each function. Go ahead and pause and do that, and then we'll come together and talk about it. Okay, so 4 is the constant, so you consider that we need all of the factors of 4, and 3 is q. So we need all of the possible p's. Oh, I should say p's. So plus and minus 1 is a factor of 4, plus and minus 2, and plus and minus 4. All right? And then the possible q's. So plus and minus 1, sorry. I wrote the number symbol for some reason. Plus and minus 1 and plus and minus 3. And so now the list of all possible rational zeros is p over q. So all the factors of p over all the factors of q. So plus and minus 1 over 1 is 1. Plus and minus 2 over 1 is 2. Plus and minus 4 over 1 is also 4. Plus and minus 1 over 3. Plus and minus 2 over 3. And plus and minus 4 over 3. So again, we've gone from an infinite list of rational zeros for this function down to 12. So these are the 12 possible rational zeros. There are no others that could that are zeros of this function f of x. All right. And then number 2, do the same thing. So this is p and this is q. 1 is q. All right. So this one's a little easier because you're basically using the second theorem there, the integral zero theorem, because the leading coefficient is 1. So possible p's are all the factors of 15. So plus and minus 1, plus and minus 3, plus and minus 5, and plus and minus 15. So go in numerical order because it makes sense to make the list in numerical order. Otherwise, you'll forget a factor somewhere. And because the leading coefficient is 1, that means the only factors of 1 are 1. So then the list of all possible rational zeros, p over q, there we go, is plus and minus 1, 3, 5, and 15, because they're all over 1. And so again, just to reiterate here, why are we doing this? Because if we're trying to find the possible rational zeros, again, we don't want to just randomly choose numbers from an infinite list. We want to choose numbers from a list that we know are possible zeros. So now we've gone from an infinite list down to 8. All right? Because it's kind of a guess and check method. So that's where we're headed now. How do we do this? Okay, I know that's kind of like a lot of, let me see if I can get, Nope, I can't. Okay, well, so these are the steps. So to find the rational zeros, once we have those possible rational zeros, we're going to test them using synthetic substitution to find which ones are actual rational zeros. So we're going to go through this example together. This takes a while, so you just have to be persistent and understand that this is a process. So we have our function f of x equals x to the third plus 3x squared minus 6x minus 8. We want to find the zeros of that function. It's a third degree function, so that means there are 3 zeros. So the possible zeros of, we're going to make a list because we want to narrow it down. So again, this is the integral zero theorem. So we have all of the factors of 8 over 1. So the factors of 8 over 1 here. So the factors of 8 are 1, 2, 4, and 8. The factors of 1 are just 1. And so P over Q, this is our list. We've gone from an infinite list to 8 possible rational zeros. All right, so we make that list. Okay, so that's the first step. Use the rational zero theorem. There's your list. Now, the next thing we're going to do is use Descartes' rule of signs to determine how many positive and how many negative real zeros. So remember, f of x, actually, I want to give myself some space here. So I'll go up here. So f of positive x, we have positive, positive, negative, negative. So how many sign changes? We only have 1, right? We have 1 sign change. So 1, that's exactly how many positives. We have 1 positive root. And then f of negative x, we change the odd degree. So this is going to be negative. This will stay positive. This will become positive. And this will stay negative. So we have 1, 2. So we have 2 or 0. So for f of negative x, we have 2 or 0. So the possible roots, we can have 1 positive, 2 negative, and no imaginary, because remember it has to equal 3. Or we can have 1 positive, no negative, 2 complex equals 3. So why do we do this? Well, here's my reasoning. Descartes' rule of signs tells me I have exactly 1 positive root. Okay? So in this list of plus and minus 1, 2, 4, and 8, I now know that there's exactly 1 of the positives that's a root. So I'm going to find that one first. Now I have a possibility of 2 or 0 negative roots, but if I try the negatives, I could get lucky. But then if there's no negative roots, there's 0. That's a risk I take of using synthetic substitution 4 times to show there's no negatives. So I don't want to go there. I'm going to test or find the 1 positive rational root because I know it exists. So because there's exactly 1 positive rational zero, I will find that one first. So that's the reasoning, all right? So I'm going to go and test using synthetic substitution the positive real roots. So I'm going to test the positive 1 first. So I'm going to do this very organized, positive 1. And the coefficients of this function are 1, 3, negative 6, negative 8. Now remember that if the remainder is 0, then 1 is a root of the function. So I need to find out if 1 has a remainder of 0. So add 1 to nothing, that's 1. Multiply, that's 1. 4, 4. Negative 2, that's not going to work, is it? That's negative 10. So I'm not going to erase it because I want to remember I tested 1 and it's a no. Okay? So now I'm going to move on to positive 2. And so it's just a little process here. So add down 1, multiply 2, 5, 10, 4. Oh, look, 8. That's 0, isn't it? So we know x equals 2 is one of our roots. So how do we find the other root? Well, guess what? This was cubic. So this is the depressed polynomial. Hopefully I have enough space up here. Of, if I can move that. Nope, I can't, sorry. So this is x squared. Just go up here. X squared plus 5x plus 4 equals 0. Remember that depressed polynomial? Depresses by a factor of x to the first, so it becomes x squared. Now, if I can factor that, which it is factorable, thank goodness, we will. So you're going to either factor or use the quadratic formula or complete the square. But this is factorable. It factors into x plus 1 and x plus 4. So you're going to factor or use quadratic formula or complete the square, whatever you want to do with a quadratic. So then use the zero product property and solve for x. So x is -1, x is -4, and we already found the other x is 2 using synthetic substitution. So in this case, there are 3 real roots. There are 2 negative. There was a possibility of 2 or 0, but we found there are 2, exactly 2, and negative roots and 1 positive root. All right. This next one is pretty good. So, and then we'll end. We have 2 more examples. So I have one with you, and then you'll do a your turn. So this one's kind of lengthy because it's a 4th degree polynomial function. So there's going to be 4 roots. 60 is your p, 2 is your q. So we're going to start off with the rational zero theorem. Okay, I'm just going to go RT, rational. Oops. RZT. I'm going to abbreviate here. Rational zero theorem, just so I can save some space and time. So all of the factors of 60 over all of the factors of 2. So here we go. It's going to be a long list. So all of the factors of 60 plus and minus 1, 2, 3, 4, 5, 6, 7, no, 8, no, 9, no, 10. So then I know I'm going back because 6 times 10 is 60. And then it's going to be 12, 15, 20, 30, and then 60. So a long list. The bigger that number and the more factors it has, and a long list. Q is just plus and minus 1 and plus and minus 2. All right. So your total list here, your list of P over Q is plus and minus 1. So all of the P's over 1. So plus and minus 1, 2. I'm actually just going to erase the plus and minus and just know it's there just to make this a little more easy to read. So plus and minus 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60. And then 1/2. And then we don't repeat. So we have 2 over 1, which is 2. 2 over 2 is 1. 3 over 2. 4 over 2 is 2. So 5 over 2. 6 over 2 is 3. 10 over 2 is 5. 12 over 2 is 6. 15 over 2. And 20 over 2 is 10. 30 over 2 is 15. And 60 over 2. Okay, good. So there's our list. That's a pretty long list. Whew. So it's going to be helpful to use Descartes' rule of signs because that's a huge list. So next step is, I'm just going to abbreviate it, Descartes' rule of signs. All right. So f of positive x. All right. So we have positive 2, negative 13, positive 23, negative 52, positive 60. So how many sign changes? Oh my goodness, we have 1, 2, 3, 4. So that means for f of positive, I want to put a positive sign there. So positive roots, we have 4, 2, or 0. Because remember, it goes down by an even number. All right, f of negative x. We stay positive. Now we turn positive, stay positive, turn positive, stay positive. There's none. So there's 0. So negative roots are 0. So that's helpful. So negative roots, 0. So that huge list has gone down by half now because none of the negatives are a possibility. So that's good, okay? So we're only going to test, so only test positive P over Q. So that's why we use that in partial signs. So we start our synthetic substitution now. Okay, so number 3, synthetic substitution. This is a long process, and I'll tell you, I started with 1 and I just kept going. So here's starting with value of positive 1. We have 2, negative 13, 23, negative 52, 60, and we add down to multiply negative 11, negative 22. Oops, that's not negative, excuse me. See where I already made a mistake. That's 23. It's negative 11, there we go. 12, 12, negative 40. Already can see that's not going to be 0. Nope. Okay. So move on to 2. Now here's the deal. I'm going to skip the process because you should understand that I went on to 2, didn't work. I went on to 3, didn't work. I went on to 4, didn't work. All right. So just to save ourselves some time, this is what it would look like though. I would show you all that. However, 5, 2, negative 13, 23, negative 52, 60. All right, 2, that's 10, negative 3, that's negative 15, that's 8. Sorry, that's 40, that's negative 12, and that's negative 60. Yes, that's 0. So that works. So now, here's the deal. I have that depressed polynomial. So the depressed polynomial is, I'm going to erase these guys just for some space. You have more space on your paper, I'm sure. So now I have 2x cubed, because it depresses by a factor of x to the first, minus 3x squared plus 8x minus 12. Now, you can now, again, because we have 1 positive root, so that means there's going to be 2 positive roots, right? Because we know for our positive roots, we have 4, 2, or 0. Well, we don't have 0. We have either 4 or 2 so far, okay? So since we have 1, there's going to be another 1 or 2 more after that too. So you could now use synthetic substitution for your new polynomial with coefficients of 2, negative 3, 8, and negative 12. We already know that 1, 2, 3, and 4 don't work, but 5 did. So then you would keep going down your list and start with positive 6, etc. However, okay, so here's the deal. You can do that, but I noticed something about this function. I am going to try factoring by grouping. Okay, so I'm going to keep the groups the way they are because I noticed something. So we're going to try a little grouping here. So out of the first group, I can factor out an x squared. And I'm going to have 2x minus 3. And out of this group, I can factor out the greatest common factor of, it looks like 4. And then I'm going to have 2x minus 3. And that worked. So it is factorable in this case. So I have x squared plus 4 is the first factor, and 2x minus 3 is the second factor. And I set each factor equal to 0, so it worked, yes. And now we're going to use the zero product property, that x squared plus 4 equals 0, 2x minus 3 equals 0. So over here, we subtract 4, and that is going to be imaginary because I'm going to take the square root, and I'm going to have x equals plus and minus 2i, okay? Over here, I'm going to add 3 over and divide by 2. So that's going to be 3 halves. And then our other root was 5 that we found. So we have our 4 roots. We have the 2 real, which is 5 and 3 halves. They're both positive, right? And then we have the 2 imaginary, plus and minus 2i, the conjugates of each other. So it was kind of a scary looking problem at first, but as you work through it, again, the key is persistence. You can't give up. There's places to make errors, obviously, and that's going to throw the whole process off. So you've got to be cautious with your arithmetic. All right, and then finally, here's a your turn. It's a little easier this time, so go ahead and try it. Work that one out. Okay, we're going to start with the rational z rational zero theorem. So P, all of the factors of 28. So plus and minus 1, 2, 4, 7, 14, and 28. And Q, plus and minus 1 and 2. Awesome. So your list, I'll do the list up here. The list of P over Q is plus and minus 1, 2, 4, 7, 14, 28, and then 1 over 2, 2 over 2 is 1, 4 over 2 is 2, 7 over 2, 14 over 2 is 7, 28 over 2 is 14. We already have those in our list. So there we go. We now have narrowed it down and we have our list. 2, we're going to use Descartes' rule of signs. All right, so f of positive x, we got positive, negative, negative, positive. So how many sign changes? 1, 2. All right, so positives, we have 2 or 0. Okay, f of negative x. Let's see, we got to change the first kind because it's x to the third. So negative, negative, positive, positive. So we only have 1 sign change right there. So negatives, we have exactly 1. So remember, if there's exactly 1, that's the one you want to try the negatives, all right? So using synthetic substitution, we're going to test negative P over Q. So we want to test the negatives. Using our synthetic substitution. So that's the third thing we're going to do is the synthetic substitution. So we're going to start with negative 1. And so we have 2, negative 7, negative 8, and 28. And so 2, and then negative 2, negative 9, positive 9. That's not going to work, is it? 1, negative 1. That one's not going to work. Okay. How about negative 2? We've got 2, negative 7, negative 8, 28. Add down 2, negative 4, negative 11, 22. Oh, what did I do wrong here? Oh, no, that's right so far. Okay, 14, sorry. That one is good. We have a 0. Okay, good. This one is our one negative real root. So we don't have any other negative roots. We could have 2 or 0 positive roots, which means now we're going to take this depressed polynomial right here, and I'm going to rewrite it up here. So we have 2x squared minus 11x plus 14 equals 0. And remember, always try factoring first. So that's where I'm going to go. And this is a factoring by grouping type of problem. So we drop down the ends, 2x squared plus 14. We multiply 2x squared by 14. That's negative 28x squared. What factors of negative 28x squared would add to a negative 11? That would be negative 4x and negative 7x, right? So negative 4x and negative 7x. That adds to negative 11x and multiplies to positive 28x squared. Awesome. So we're going to group these guys together and group these guys together. So I can factor out a 2x, and I'm going to have x minus 2. And I can factor out negative 7. I'm going to have x minus 2. There we go. So I have 2x minus 7 times x minus 2. And using the zero product property, 2x minus 7 equals 0, x minus 2 equals 0. So x is going to be add 7 divided by 2, 7 halves, positive 2, and negative 2. So hopefully you found that one to be a little easier than the last problem, but it is, again, just the same process. So you've got all these skills, you're putting them together. It helps to have those steps in place so you are not overwhelmed as to where to begin, all right? So make sure you ask good questions during class, and I'm happy to help you.